Hi, this is my video number 35, and I think this is might be the last video I'll be made. Okay, yesterday in the previous video I have discussed the basic properties of mellin transform, where it is not difficult to prove all these things. Yeah, you have 4-5 properties. It's not difficult to prove. You can do this thing. And as well as I have discussed the possible formulation for the mellin transform, which is given by this, yeah, integration of multiplication of two function is given as that. Okay, now as promised in this video, I'll give you example. Maybe in this example some of them I will skip because I think it's too hard to follow, right? This example number 1, this is pretty simple to do it. Okay? So let's say we want to we consider the exponential integral given by this ei integrate x to infinity with all those things, and change of variable, you can have those things. Yeah, just consider u equal to qx, then you can have those that line, right? So the mellin transform of the exponential integral is given by that. So we have, this is definition of mellin transform. We have x s minus 1 fx dx, where your fx is given is here, that, and then just rearrange that things, and that give you the again change the variable qx as a u, then you can come up with that. Okay, so this example seems pretty hard to follow. I think I just skip that one. But maybe some result here we might need, then we can just refer to that result. Next example, we consider the mellin transform of the real value function fr. Okay, so we consider this the mellin transform of that function f rei theta, right? So by definition of mellin transform, we have those things. So if we take z equal to r e minus theta and do substitution into that, and this function is analytic continuation of a function of r defined in some sector argument of z between minus alpha and alpha. Thus you can write those integral as this, right? So you have what we do here is this part and this part is just 0. Actually we just minus plus the same thing. Even if you look at the limit is different, the limit here, then we take a limit goes to infinity, we take r goes to infinity, all right? And then this part here we can integrate over the contour c is given by this, yeah, just by changing the variable z equal to r e I theta. So you can have those things, and then it will end up to that equation. Okay, then provided that the integral along c goes to 0 as r goes to infinity, what we have now, because this part is 0, right? This part is 0, so what we have, this part is equal to that. So we have that equal to that, and this integral is given this integral we have e minus I s theta, that one, and this is the definition of mellin transform for the function f, which is given by that. Okay, so in order to have this, yeah, in order to have to obtain the things on the right side here, yeah, the sufficient condition for this is that z to the s fz goes to 0, fz goes to 0, for z goes to infinity for the argument of z less than alpha. So then because of that, we have rs fs fr goes to 0, and we use this property here in order to evaluate that part is 0. So that's why we have this part is 0 here. Okay, and then here's some typing error. Should be 0 to infinity f(re) I theta. This is given by that. So this is what we obtain from here, right? This is what we want to evaluate, and then give that and that. Okay, and then if we consider the real and imaginary parts, so we going to have